Hello again to my YouTube channel. Today in this session, I will continue to discuss with you the logistic regression as a word of classification problem. So today I will show you the metrics, so how we can measure the performance or the accuracy of model. So as we see before in the last session, when we starting or we discussing in this linear regression algorithm, I show you the formula of this algorithm. Okay, and um, why we need to squash the straight line. The linear regression, we cannot use it to solving this kind of problem. I mean the classification problem, because for enough reasons. The first one is when we have outliers, that means the best fit line, it will be changed to minimize the distance between the new points we have and the straight line. So for this reason, the old point it will be changed. So as I show you in this theoretical example with pass and file, well, um, also we have the problem of the values. Okay, the linear regression use it just in continuous values. Sorry, does not work for discrete values. Okay. Also, when we have a threshold, the new term or the new values here, the predicted one or the outcome of some values, it will be more than one, for example. At this time, how we can consider it? What is the class will be associated with these values? Well, today, so and I show you the equation behind the logistic regression is a sigmoid function. Okay, we have the equation of a baseline, and we squash to make all the values arranged between 0 and 1. Well, today I will show you the matrix, because of course we need a matrix, how we can know if our model is based or not. Okay, we need some matrix to help us to do this job. Also, here in this last section, I show you the loss function. So does not work. The loss function in logistic regression. Sorry, in the linear regression does not work, because when we replace our after squatching our model and replace this equation inside of a sigmoid function, does not will work. Does not will give us this convex function. Okay, at this time we can find a local minima. That means we have small values, and at this time our function or our conversion does not will be work, because use does not time we can paste it here in any place for here, and our purpose is to find this global minima. Well, this is the equation behind this update. Well, let's continue to see this matrix. Well, the first thing before passing to matrix, we have a regularization. So what we mean about regularization? So as we know, if we collecting our data and try to dividing this data into parts. So when we collecting the data as I did before and gave those data to my model at this time, okay, the process, because in the some last session when we worked to implement a model using PyTorch, uh, okay, I show you how we can implement. Okay, the first step is collecting the data, and the second step is to splitting the data. That means, so we cannot give all the data we have for my model, or to my model, sorry. We need to split, we need to divide those data, to split, to training, and to testing. Okay, the same the process. Uh, how does work? We need to dividing my data to training and testing. Well, when I give for my model the part of training data, I mean maybe 20% of my data to my model. I train this data, I predict it, I measure the performance of my data. At this time, we can face a problem called the overfitting. Okay, overfitting. That's mean overfitting is just so to make it easy is when we give the part of data of my model. Okay, the accuracy when I measure the accuracy of my training data, it will be more, maybe 90% or something like that. But when I give it for my model part of this data, the accuracy it will be less than the accuracy of training data. At this time, that's what's called the overfitting. Why this overfitting is coming? Because my model it's captured all the pattern of data. It's recognized the data. It's now the pattern of data. At this time, we give for us this high accuracy. Okay, but we have a technique to reduce this overfitting. That's what's called L2 norm. L2 regularization is for reducing overfitting. And we have other techniques, L1 regularization for feature selection. I will show you, discuss later that. Here, as I said before, we have L2 regularization. What is the equation behind? So let's show you here. So we have L2 regularization. This is the cost function here equal to minus y log of h of theta x minus 1 minus y log of 1 minus h of theta x plus this second term. This second term, that's what's called organization. We have here alpha, sum of all these elements we have starting from 1 to n. That means we have a lot of features because when we're working with these models, of course, here in this tutorial, I work in just one feature. We have independent or target feature as well. It's called y, and we have the other one. It's x, for example. In real projects, we're gonna facing a lot of feature, a lot of variables. Okay, for this reason, we have this sigma all the elements we have. So we have lambda times the sum of all these elements, slope squared. Slope does mean slope of equation. So as we know, we have, if we consider this equation, y equal to uh, theta 0. Okay, sorry for my writing. I have electronic pencil for the my writing is not clear, but it's okay. We have theta 1 times x. So as we know, in a linear regression, we have this equation to draw a straight line. This is the equation behind this straight line. Why? We have the slope here. This is the slope. That means if we go in the x-axis with y steep, how much I need to increase my straight line. This is what's called the slope of straight line. So I will show it here. Sorry, in this graph. Okay. Well, so here in this example, if we take in this straight line, so we have slope. The slope does mean if I go one step in this axis, how much I need for y-axis to decrease my straight line. This is what's called slope. So here in this technique of reducing the overfitting, why we use that? Because as I told before, if we have accuracy is high, maybe 90%, that means the error is very small. It's very close to zero. But for us in this training, we don't want to have this measure, this small value. For this reason, we need to add in second terms. That's what's called the L2 regularization. So here we have this value here in this training. It's maybe is close to zero, or maybe it's error is zero. Okay, it can be zero. That means we have zero errors. all the points projected is in the same straight line. We need here to add in the second term to avoiding this zero, to give also the ability for my cost function to update and they give me the new values. Okay, here this lambda it's hyperparameters. It's hyperparameters. Any sorry for Arabic. Well, that means we don't need to choose this random value for lambda. We need to choose it by some strategies. I will discuss it after. Well, this lambda is hyperparameters. Okay, can it be one? Can it be two? Can it be 1 point? That's different. And we have the slope of all these features, all these lines we have. It will be squared to give me a new values to update it in my convergence algorithms in gradient descent. Okay. Well, also we have a problem of L1 regularization. Why that is important? Because we need to feature selection. Because in a problem, in real problem, your data set, after I will show you when I go to implement these things with Python. Well, here why I need this technique of L1 regularization, because I need to choose the feature selection. What is mean feature selection? Okay, so let me do something here. So in my model, for example, I can have more than one feature. This is theta 0 plus theta 1 x1 plus theta 2 x2 here theta 1 and also theta 3. Okay, I have theta 3 times x3. Okay, let's take in let's consider just three feature. So here what's happened is each of these parameters theta 1 and theta 2 and theta 3 has its own slope, because this is equation of our model, because we have high dimension. So each feature of all these main model is considered as a dimension. At this time, maybe can I face in 10 or 12, or that's depend number of dimensions I have. Here, the goal of this technique is to choose all the slope of this equation, theta 1, theta 2, and theta 3, and they need to pass it to absolute value. At this time, I need to choose just the important slope. Okay. So if, for example, this theta 1 is 0.05, for example, for theta 1, and for theta 2 we have 0.41, for example, and also for theta 3 we have 0.6. As this time, I need choose just both to theta 2 and theta 3, because that is important. It's more important than 0.05. 0.05 is small step. That means if I go one step for my x-axis, in this example, the step to the step of my slope here in this equation is 0.05. That means it's a very small step. It's not important based on my regularization. I will go just behind this one and this one. I may be kind of facing a negative ones. Okay, so for this reason, we apply absolute value here. Maybe kind of facing a negative slope like this. In this example, the slope of this straight line is negative. Okay, here slope of this equation, or slope of this the slope of this sorry the slope of this line, straight line, it's negative because it's go in the opposite sense. So for this reason we apply this absolute value to make it positive and measure and see what is important one. At this time, we chose just the important one. Okay, this is the L1 regularization, and we have L2 regularization, but we have also sometimes called elastic. So elastic here, elastic net regularization does mean I consider both of these norms, L1 and L2. I consider both of these regularization. I apply L1 and also L2 here. This is my cost function. Then I added this slope squared and the absolute value of slope. I called both of those regularization. So uh, I hope understood. So that will be clear when we try to implement the model using Python. Well, here we passed in this axis of performance metrics and accuracy and precision, recall, and F beta. Well, as I told before, when we implement our model, we need something, some measure, give me the ability to consider my model is best or not, the accuracy of my model is good or not. How we can do that? One of these measure in this problem of classification, we have sometimes called confusion matrix. So as we see here in this so here we have 0 1. At this time we consider just binary classification. That means we have a problem with two output, 0 or 1. Here is considered like actual value. That means the real data we have, the actual y, or the real value of y. And here is the predicted one. The predicted does mean y hat. And here is the intersection between the actual and uh, the predicted y, or predicted y hat. Well, if we consider this small data set we have here, we consider some features x1, x2 with some values here. Okay, we don't know it, but what is important here is the predicted and the actual value. Here, y is actual value. That means the real data we have, because as we know in the supervised machine learning, first type, especially in the classification problem, we have labels and the data. That means we have the answers. So in this training, for example, data or test, we check those results, and we found in the y, here we have this result. We have 0 1 0 1 0 1 1 0 1, and the predicted one here is 1. So after training of my model, the predicted is y hat. We have 1 1 0 1 1 1 1 1. Well, the confusion matrix help us to measure how is how this model is wrong. Well, if we consider the first row here, we have y. The actual value is 0, but the predicted one is 1. That means this prediction is wrong. Here, as I said before, we have 1, 0, and 1, 0 actual value and predicted value. Well, if this value here is 0 in the actual value here, in the actual y, that means here, okay, we have 0, okay, and is predicted as 1 here. It's predicted as 1. That means the intersection between 0 and 1 is here. So I put 1 here. I put here 1. This is why it's wrong 1. I put it here. And I passed the second one. We have 1 1. That means the predicted it's correct. I go to this intersection between y predicted and actual, and I pass here 1. This is 1. It's okay. It's considered 1. I go here again. We have 0 0. That means correct prediction. So here we have 0 and we have 0. This I put it here. This intersection between 0 0 is here. And also we have 1 1. We added 1 to the last one. That means we have 2 here. Okay. Also we have 1 1. That means it's 3. We have here For actual, we have 0 and we have 1. 0 actual and 1 is predicted as 1 also here. That means we have here 2. Will be 2 here. And also we have 1, 1. That means it's correct prediction. Okay, is 4. Okay. Well, how we can measure the accuracy of our model? So let's see firstly this notation. As I said before, this confusion matrix, we have actual and predicted. Here, the intersection between the actual for 1 and predicted, that's called TP. That means true positive. Okay, true positive here. True positive. That means the actual value is 1 and the predicted 1 and the predicted here is 1 also. That means this intersection gives me the true positive. Okay, we have here 0 and we have here 1. That means the actual value is 0 and is predicted was considered like 1. That means false positive. Okay, this is false positive. Also, we have here 1. Okay, the right value is 1, but it's considered on my model is 0. That means it's wrong prediction. That's called false negative. False negative. We have here 0 and also is predicted 0. That means wrong, correct prediction is true negative. True negative. So to measure my model, this is the formula. True positive plus true negative. That means true positive here plus true negative divided by all these things. That means true positive plus true negative divided by true positive plus false positive plus false negative plus true negative. If we consider our example here on the top, we have 3 plus 1, or here it's 4 because based on this data I correct this, where we have 4 because here 1, 1, 1, 1. That means we have 4. And also for this we have 0, 1. So 0, 1, this is 1, and this is 1. That means 2. Okay, that means 2 here, but we have here 0 and here 0. It's okay. So let's work on this. Let's consider 3, 4. Okay, so let's consider this 3 and 4. Well, so to consider or to measure my accuracy is 3 plus 1. Okay, 3 plus 1 here. True positive plus true negative divided by 3 plus 1 plus 1 plus 1. This is here. Okay, 3 plus 1 divided by 3 plus 1 plus 1 also plus 1 here. Okay, equal to 4 divided by 7. Okay, 4 divided by 7 is equal to 0.57. I'm sorry again for my writing is not clear, but I try to do my best here. So equal to y equal to 75%. Okay, so the accuracy of my model is 75%. Okay, so how this is how we measure the performance of my model. Well, we have so TP and TN, that means true positive and true negative is correct match, and false positive, false negative is wrong match. Well, so when We collecting our data. Sometimes you're gonna facing a problem of imbalanced data. Imbalanced data, I will show you a small example here. So let's consider this data set. We have imbalanced data set here. So let's consider 1000 point or 1000 record. So when we check in this, because we found we have 900 of class 1 and we have just 100 for 0. This is, we are in the case of imbalanced data. Why that is imbalanced data? Because when we pass our model for training, we can measure the accuracy and it just will be capture the first one. That means most of time, if the new data is coming to my model, in most of case, it will consider it like a class 1 because we have here 900 and 100. That means if some new point is coming to my model, we have the probability to consider it 9 times 1 more than 0. So here, if we try to measure the accuracy, is, so consider this confusion matrix here. We have 900 of class 1. Okay, it's predicted also as class 1, but we have 0 for class 0. We have 100. The accuracy of this model is 900 plus 100 divided by 1000, 1000. Okay, to find this accuracy. So we have 900 plus, or this is 100 divided, this is accuracy 900 divided by 1000 is give me 1900. Is given 1900. So when we collecting the data, we have the probability to facing this problem of imbalanced data. At this time, we need to call a technique called oversampling. Oversampling does mean we are regender the other data to be make it more imbalanced. So at this time, if we are taking this oversampling, and we found, for example, we have here 400 for class 0 and we have just 500 for class 1. At this time, is it will be considered like a balanced data. It's not imbalanced. It's considered like a balanced data. So if we consider this model at this time, it will be not sufficient because we have two class 1 and 0, and the most time it will be predicted like a class 1. So that is not will be good for our model. So also we have some concepts. Here we have precision and recall. So precision measure the accuracy of positive prediction. Okay, this is the precision. This is the formula of precision. Precision is simply is true positive divided by true positive plus false positive. Out of the actual values, how many are correctly predicted? That's mean here. If we go to my matrix, so let's go to top. Here, in this case, if we try to see what is the precision here, the formula is true positive divided by true positive plus false positive. This is the formula here. Okay. Well, that means here, out of all these actual values, all actual values here, because we consider all these things, because we divided true positive, or true positive divided by true positive plus false positive. At this time, we consider all this output of my actual data. At this time, all of my actual data, how much is correct predicted. This is the precision. Okay, the precision is here at this time. We go here in this sense. The true positive divided by true positive plus false positive. Out of all these actual value, how much is correctly predicted. This is precision. And also we have another formula called recall. Number of correct post prediction made out post prediction that's called have been made. So recall is true positive divided by true positive plus false negative. True positive divided by true positive plus false negative. Out of all these predicted value, how wrong are correctly predicted with actual values? Here we consider the matrix with small example. The recall is here because the formula of recall is true positive divided by true positive plus false negative. That means out of all this predicted value, because here in this part is predicted values, how much is correctly predicted? So based on this predicted one, how much is predicted? Well, so we have a note here. Whenever false positive is important, we will precision. That means we reducing we reducing this false positive. When we facing some scenario, we need to focus just for false positive. At this time, we need to reduce the false positive. Whenever false negative is important, we will use recall. That means at this time we need to reducing the recall or reducing this false negative. Here in this recall, we need to reducing this false negative. That depend of scenario we have. So here, if we consider this, so if we consider this use case for spam classification, that means we try to build in a filter for classification. Spam classification does mean we consider here precision. So we have text. Okay, we have a text. Give it for my model, and it's predicted it will be spam or not spam because this binary classification we have spam or not spam. So at this time here, if we check in our confusion matrix, actual values here is 0, 1, and predicted one here. We have true positive, positive, false negative, and true negative. At this time, true positive is 1. It does mean it's spam. True positive does mean it's spam. It's saying it with 1. Mile, it's a spam. I give it to my model. It's predicted as spam. Accurate. And other one here we have not spam. We consider it is a true positive. That means 0. Give it to my model. Is considered not spam. Okay. Here. So mile. Here my mile is coming and is not a spam. Okay. But is considered as spam. That means it's not correctly predicted. Okay, we give it to my model. It's considered as spam. It's not spam, but it's considered by my model is a spam. Is wrong prediction. Wrong prediction here. Okay, and also and sometimes my mile it's coming and it is spam. It's a spam, but my model is considered not a spam. Okay, at this time the precision here is more important. Why? Because if my mail is coming here considered like a spam, is not is a spam. Okay, but is not is considered log is considered not as spam at this time. So we cannot check because the precision here is more important. Okay, in case in our case the precision is more important. Okay, that means we need to decrease this false positive. We need to decrease. Okay, we need to decrease this because in precision true positive divided by true positive plus false positive. That means we need to decrease this false positive because it's a because here is not considered as spam. It's not a spam, but it's predicted as a spam. Okay, it's not a spam. Considered as a spam. That means we need to decrease this. Okay, we need to decrease this false positive. So let's pass into another use case here to see the importance of recall. So in the medicine field, so false positive is important. That means the recall is important. So to predict person has a diabetic or has a cancer or breast cancer for women is more dangerous. Maybe this scenario is more important. Okay. Well, let's consider these diabetic people. We have diabetic and not diabetic. We have diabetic and not diabetic. So for actual and for the predicted. Okay. The actual value of true positive is diabetics. My model is constituted like a diabetic. That means it's correctly predicted in this first scenario here. This typical true positive. For true negative also, those people is not diabetic as it's predicted not diabetic as we see here. Not diabetic. My model is predicted not diabetic. That means it's correctly predicted. Here for false positive, we have actual, okay, not diabetic, but my model is considered like a diabetic. Is wrong prediction. Here is my actual. That means is diabetic. In my actual data is diabetic, but my model is considered like not diabetic. Well, is a problem. Here in the last case we have if false negative is diabetic, my model considered like not diabetic. Okay, it's blender. My model here is blender. So at this time, the recall is more important. The recall is the formula of recall is true positive divided by true positive plus false negative. So we are considering in this part. Why? Because in actual data here we have all these people here in this part. It's diabetic. Okay, and my model is considered not diabetic. That will be a problem. That will be a problem really because if the people has diabetic and my model considered like not diabetic, it will be dangerous. So there is no need to focus on this recall. That means we need to reduce the false negative. We need to reduce the false negative. Okay. So I hope that it's clear for you. I will show you examples, of course, when we try to work in data. I will show you all these things and how it is important and how we can work with. Well, also we have another metric. It's important. That's what's called if beta score. If beta score is interested of both of the measure, recall and precision. So in this scenario, if beta score, this is the formula firstly. We have 1 plus beta squared precision times recall divided by precision plus recall. This is the formula of beta score. So if false positive and false negative are both important, that's mean. So where is the formula? Yeah. So if this and this important for us, we are care for false positive and false negative because in this formula, what is the purpose is to decrease this false positive and false negative. So if we are interested in both of those measures at this time, what we can do here based on this F score or if beta score, we need to assign for a beta 1. That means the beta we give it or we give for this beta 1 as a value. At this time, if score it's coming if score 1, it's not beta. So if beta score, beta here we give it 1, that means it's coming if 1 score. If 1 score equal to 1 plus 1, that means 2 times precision times recall divided by precision plus recall. So we can have facing some scenarios. We need to consider both score and precision and recall at this time. For example, if tomorrow I will tell you tomorrow the markets will be crashed. Tomorrow the markets will be crashed. So both for industry and for people has the ability to trade or for traders. So for traders will be care about precision, and but for industry it will be care for a recall. At this time, both of recall and precision is necessary. At this time, we can use this if one score. Okay, we give for our beta 1. Well, if we pass for the thyroid case, so if false positive is more important, so uh, in case of spam filter, as we see before, at this time we can send as a value for our beta is 0.5 because we are considerate we consider just false positive. At this time beta is equal to 0.5. So if we replace 0.5 in our formula, we can get this value of 1 plus 0.25 times precision times recall divided by precision plus recall. Okay, this is the result we get. Well, the third scenario, if we are just care about false negative, that means we need to reduce the false negative. That means the recall. At this time, we need to assign for beta this value of, at this time, we need to pass this value of beta equal to 2. Okay, the beta is equal to 2. Well, if 1 equal to 1 plus 2, 2 squared here is 4. 1 plus 4 is 5. 5 times precision times recall divided by precision per recall. So if we consider if we consider this false negative, at this time we can pass this value of beta equal to 2, and we get this formula. Okay, three scenario. For one, if we care about both of these measure, we pass beta 1, and for recall we pass 0.5, and for precision we pass 0.5, and for recall we pass 2. So I hope that's clear for you. So in next session we talking about hyperparameters, how we gonna choose in our parameter for some model. Well, I hope so. Happy learning for everyone again. I hope that is clear for you. Okay. See you in next session. Bye bye.